In this video, we'll cover the problem concert convergence. You'll be given two inputs. The first is a number n, which tells you how many cities we're dealing with. They're labeled 0 through n minus 1. The second is an array of roads that tells you how you can get from one city to another. So in this question, there's a huge concert happening in city 0, and everybody's trying to get from whatever city they're in into city 0. So what you need to answer is how many roads need to be flipped so that every city has a path to city 0. So in this example, if we start with the 0 node, of course, city 0 can reach itself. From city 4, it looks like there is a route right here from city 4 to city 0. So city 4 is good. City 5 does not have a path to city 0. So we're going to need to flip this road so that we can go from city 5 to city 4, and then from city 4 to city 0. So now city 5 is good to go. Now if we go look at the 1 node, I should have mentioned the 0 node is good to go, but that's intuitive. All right, city 1 cannot reach city 0, so we're going to have to flip this road right here. Now city 1 is good to go. City 3 cannot even reach city 1, so we need to flip this. And now city 3 is good to go because it can reach city 1 and then reach city 0. City 2 can reach city 3, and assuming that we have flipped these two roads that we're supposed to flip, then city 2 should be good to go, so we can go ahead and check it off. So you can notice that I've circled 3 different roads that need to be flipped, so our output right here is 3. Okay, so really we want to make sure that every city has a path to city 0. Well, the edges I circled, if you notice carefully, are these 3, which are the edges that are pointing away from city 0. And if you think about it, that kind of makes sense. If everyone needs to get to city 0, then every edge should be pointing towards city 0. It doesn't make sense to have an edge that's pointing away from city 0. All of those edges will need to be flipped to point towards city 0. So this problem really comes down to counting how many roads are pointing away from city 0. So let's see how we can figure that out. If we just pick any particular node, let's say we're at the 3 node, and we want to say, like, hey, are my edges, these two edges, actually, I'll just point to them. So, no, okay, so we'll do this. We're currently at the 3 node. The 3 node has 2 edges. This first one is going to the 1 node, or is like between the 3 node and the 1 node. The second one is between the 3 node and the 2 node. How do we check if each of these edges are pointing away, toward or away from the 0 city? Well, we don't really know because we have no idea where city 0 is. But it's possible that city 0 is over here, in which case this edge right here is totally valid, but that's not accurate. But the 3 city doesn't know where city 0 is. So that's not going to work. Instead, what we can do is sort of build up our solution starting from city 0. And that way we have a general idea of where city 0 is. So as an example, we start at city 0, of course we know city 0 is valid. Then we come over here to city 1. Or actually no, at city 0, we know where city 0 is. So what we can do is say, all right, check all of the edges and make sure all of them are pointing inwards toward me. This one is fine. This one is not fine. It's not pointing inwards. So we say, all right, this is one that needs to be flipped. I'll track some tallies over here. So this is one road that needs to be flipped. So we're at the 0 node, we realize, all right, this one needs to be flipped, and we're good to go. Now we go over to the 1 node. In other words, city 1. When we're at city 1, we now know that we can reach city 0 because city 0 has flipped the road and we're good to go. So we know that there is a path from city 1 to city 0. This is valid. So I'll mark that with a check mark on on city 1. Now we can repeat the same process. So we can look over the edges for city 1, which this one we don't need to worry about anymore because it's already taken care of. But this edge has not been processed yet. And what we can do is we can, instead of asking, does this edge point towards city 0, we can just ask, does this edge point towards me, the current city? Because we know that from city 1, we can get to city 0. So as long as city 3 is pointing to city 1, city 3 has a path. But if city 3 is pointing, if the road is pointing away from city 1, then it's not valid. So what we can do is sort of use 1 as a proxy to figure out if this particular road is pointing in the right direction. That way we don't have to know exactly where city 0 is, but we know where city 1 is. Okay, so this general idea is at each node, we explore all of the roads that go that are like touching that city, and we see how many of them are pointing away from me, the current city. All of those are invalid. So in our case, this one is another invalid road because it's pointing away from one, so we bump our tally. Then we come over here to the 3 node, the 3 city, city 3, and we explore its edges. We know this edge has already been processed, we don't need to worry about it. But this edge right here has not been processed. So we ask ourselves the question, is it pointing inwards? Is it pointing to me, which is the 3 city, city 3? The answer is yes, so that one is totally valid. We don't need to count anything else. So for this portion of the graph that I'll sort of outline right here, there are exactly 2 roads that need to be flipped, which we see from our tally count here. I'm not going to go through the entire example for the sake of time, but the same process applies for here on the left. Okay, so all this makes sense. One question that's important is we need to know if a road is pointing into a particular city. Right, so we need to know that this is pointing out of city 1 and into city 3. This is something we can just go ahead and process when we're building our graph out of the roads array. We will just say, okay, if we have a road that says it starts at 1 and goes to city 3, then when you're adding it to say, hey, this is an edge from city 1, just mention it's going out. And when you're adding it as an edge for city 3, just say, hey, this is coming in, like into the city. So that should take care of knowing the directions here, and that will be helpful when we're trying to determine this information about, like, at the current city, are the roads around me going to be pointing inwards or outwards? That'll let us access that. Okay. One other thing that's important here is if you notice when we're currently at the 3 node, and we'd already processed this node, so we didn't worry this edge, so we didn't worry about it. But we wanted to process this edge, but you'll notice that it's not possible to go from city 3 to city 2, at least with the way things are structured right now. So if we just follow the natural direction of this edge, we won't even realize that we need to process a city 2, because we would only care about outward facing edges. So we have to deal with our graph a little bit weirdly for this problem. We want to say, store all of the edges. So we just want to know that, hey, there is an edge from 3 to 2, and just keep track of the fact that it's actually going into 3. So when we're at a particular node, we want to explore all of its potential neighbors and their edges, even if they aren't valid, like that direction doesn't make sense, we should still be processing them. Okay, we also want to make sure that we're tracking what nodes we've visited before, just so that we don't end up visiting the same node over and over again and getting into potential cycles. All right. With that being said, let's talk about the complexity of our solution. So we want to initially define our variables. So we'll say V is going to be the number of vertices in our graph. I'll actually write the number of cities here just to be appropriate with the context of the problem. And then we'll say E is going to be the number of roads. You know what? I'll go ahead and name these C and R. So C is number of cities, R is number of roads, but it's the same thing as number of vertices and edges. So our time complexity is going to be O of C plus R, and our space complexity is going to be O of R. So one thing I realized I actually didn't mention, that is hopefully relatively intuitive, is that we started the 0 node and then went to 1 and then to 3 and then to 2. So if we go all the way deep down one path and then come back and later handle the other path, we're going depth first. So we can use a depth first search to do our traversal here. That's where the complexity comes from, right? We know that we're we should be touching every single city because we need to verify that every city can reach city 0. So we have to have a C here. And we're also going through all of our roads because at each city we're looking at all of the roads that it is touching. So in total we're looking at all of our roads, so we have R in our complexity as well. So C plus R is our time complexity. Our space complexity comes from 2 things. First is if we look at the maximum size of our stack. If we had a graph that looks something like this, where we just have sort of a linear graph and one node points to the next, then we would have the complexity is actually wrong here. It's not O of R for the space complexity, it's O of C. In this scenario, you would just basically have every single city push on the stack at one point in time, since we're going depth first. And in that scenario, you would have C is determining how much space you use. We also have our visited set, which, by the end is supposed to contain all of our cities because we should be visiting every city. So that's another reason that we have OC as our space complexity. All right, that's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, we have this queue here. Remember, we don't need it in our case because we're using a DFS, not a BFS, but it's there in case we need to access it. Okay, so we know that the way we're approaching this question is we are doing a DFS. We're tracking what we visited, and we're saying each node, look at all of my neighbors and count how many different roads are pointing out of my current city. And all of those should be added to our counter. Now, the very first thing we need to do before we get into any of that is we need to set up our graph. So let's say we're going to write another function called build graph that's going to take in our roads array. And so this is going to be a function, build graph, which takes in some edges and is going to create a graph. So we'll just create an empty object in JavaScript and return that in the end. In between, we want to iterate over our edges. So say for each edge, what do we want to do? Well, each edge is going to look like what? It's going to look like this, exactly what I've highlighted, here. So it's an array that contains 0, 1, something like that. So we can say we've got start city and end city here, which is going to be our edge. If you're not familiar with destructuring, all I've done here is just grabbed out 2 of our values. So I'm saying const start city is going to equal edge at 0, and I'm saying const end city equals edge at 1. Just doing that in a single line like this. Now, what we want to say is graph at start city dot push end cities, right? Because we're going to have an array. So we'll say from our start city, there's an array of cities we can go to, and end city is one of them. And then we'll have the reverse as another one of our options. So we'll be saying that we can go from the end city to the start city. Remember, we're treating these as undirected edges. We don't really care about the direction. But we want to know what the direction is, but we don't want to say like, oh, you can only go from start to end. You can also go from end to start. Now, there's a couple of things we need to take care of. First is that, we're pushing, but really graph at start city might not be defined. So what we can do is we can say, if not graph at start city, then just set graph at start city to an empty array before we push. And we'll do the exact same thing for our end city, like so. So we'll copy end city and paste it here and here. Okay, the other thing is we need to be storing information about the direction, and we're not doing that here. So what we're going to do is store not only the city that we're talking about, but also a string that tells us whether the road is going in or out. So let's see here. For the start city, and it's going out of the start city, right? Because if we go from the start city to the end city, the edge is going out, the road is going out of the start city. And the opposite is true here. These are going inwards, because if you're at the end city, and you're coming from the start city, the road is going into your end city. Okay, so now we have our graph set up so that we can access the information that we need. Now let's set up the rest of the stuff we'll need for our BFS. So we know we're going to want a new set for our visited nodes. We also, let's just give ourselves some space here. We know that we are going to need the number of roads to flip here, which is going to be 0 initially, and we'll return that in the end. And of course, we're going to update that in between. Now here, we're going to do our DFS. So we'll create a stack. We will say push onto the stack 0, city 0, because we said we're going to start from there and sort of move outwards. Then we're going to say so long as the stack length is greater than 0, we'll continue iterating through our DFS. We can pop whatever cities off the stack. Maybe we can name this current city just to be more precise. Say stack.pop. We want to process our node, which we'll think about what to do in a second. And then we want to examine our neighbors. And we've seen this general skeleton many times. Now, I'm going to be a little bit more careful than normal here, because if you remember the way we talked about this in the approach was that when we're at the current city, we look at all of its edges, and that's when we determine how many roads need to be flipped. So it's actually not at the process node step that we do the core logic for this question, which is atypical. It's not normal. So we're going to be really careful here. When we're at the current city, we assume that the current city has a path to city 0 because we would have processed that beforehand. So the current city has a path to city 0. Let me actually write that down. assume the current city has a path, has a path to city 0. Really what we want to do is look at all of our neighbors and say, does this neighbor have a path to me? So we can say our neighbors is going to be graph at the current city, because our graph is mapping from a city to everything that you can reach from that city, assuming our edges are undirected, which we know that they're not. All right, the first thing we'll say is, if not neighbors, let's just go ahead and continue. If there's no neighbors that we need to worry about, just move on. Because it is possible that the current city has nothing in our graph and it was not involved in a road. Okay, now what we can say is neighbors dot, actually let's name this a little bit better. Let's say neighboring cities, just because, it's more relevant to the question. All right, so for each of these neighboring cities, what do we want to do? Well, we'll say take the neighboring city and do something. First thing I'll do is I'm going to destructure out the two properties, because remember, each neighboring city is not actually just a city. It's really an array that contains the city and the direction. So let's go ahead and say neighboring city name, or I guess number and direction here is going to be neighboring city. Again, I'm using some destructuring here, but this is equivalent to just saying const neighboring city number is equal to neighboring city at 0, and then something very similar for direction, const direction equals neighboring city at 1. That's all I'm doing on line 84. All right, now we have the neighboring city and we have the direction. Now we know that we want the direction of this edge to be pointing inwards into the current city. So the direction we set up respect to the current city, because the way we grab all these neighboring cities is by doing graph at the current city. So this is telling us the direction relative to our current city. The direction should be inwards. It should point into the current city. So what we can do here is we can say if the direction is out, just return. Which return is the same thing as a continue. It's just in for each continue doesn't work, you have to use return. But this is just saying go to the next iteration, go to the next neighboring city. And otherwise, if the direction is not out, we know the direction is in. Actually, no, hold on. This is a mistake. We don't want to return in this case, actually. If the direction is out, that means that there is a road that needs to be flipped. So we need to update our counter. We don't have to go to the next iteration. That's not necessary here. But we do want to say num_roads to flip needs to be incremented by 1, because this is a road that is pointing in the wrong direction. All right. After we do that, we still need to go to that city and sort of repeat the process, because now we know from that city we can reach city 0. And when I say that city, I mean the neighboring city. But we don't know about the neighboring city's own neighbors, so we want to process that as well with our DFS. So we'll say stack.push the neighboring city. And you can notice we don't need to include a direction, because in our stack we only have the city itself. You see that from line 67 and from line 70. Okay, this is all fine, and this is good core logic. The one thing that we're missing right now, or at least the one thing that I see that we're missing, is we're not using our visited set, and we could potentially get in some sort of cycle if we're not careful here. Especially because we're treating things as undirected edges. We could just go back and forth between the same two nodes. So, remember our process node is saying, what do we want to do for every node when we get to it? So let's just say for every node, whenever we get to it, add it to our current city set. And what we can do here is we can just say, we don't want to, well, actually, hold on. Let's be very careful about this. We don't want to be incrementing our counter multiple times for the same road. So what we can do here is we can say if we've already visited the neighboring city, so if visited.has neighboring city number, then now we can return. In this case, we're saying go on to the next iteration of our for each loop, which basically means skip this city. Because that means that we've already visited the city, and if it was the wrong direction, we've already accounted for it, so we don't need to be accounting for it again. All right, so now I believe this should be the core logic. The key idea is this, that when we're at our current node, we look at all of the neighbors. If any of the roads between the current node and the neighbor is pointing out of the current city or the current node, then we need to bump our counter because that road needs to be flipped. Let's see if this works when we run our code. All right, it does not work. So something is wrong. All right, I realized the issue. It is a subtle thing. We know that everything on the stack is supposed to be just the city number, and I realized what I'm pushing on line 90 is actually the whole neighboring city, which is an array that contains the city number and the direction. The mistake was that this needs to be neighboring city number. And if that's the case, then we push just the city onto the queue, which is what we're expecting on line 70. So if we run our code now, we get the correct output of 3. And if we submit the code, looks like it is passing all of the test cases. So we can look at those real quick. Okay, so looks like that code is correct. Let us go ahead and talk about our complexity here. So we can define C to be the number of cities, which is also equal to n, so you could use n instead if you wanted to. And we'll say R is the number of roads, which is also the length of the roads array. We can say that. So time complexity is going to be O of C plus R. Our space complexity is going to be O of C. So time complexity, we know that every city is going to be pushed onto our stack at some point in time. So we have dependence on C for our time complexity. And we're going through all of the roads because for each node, we go through all of its roads, which means in total, we go through all of the roads. All right, for the space complexity, there's 2 reasons that we have O of C. The first is in the worst case scenario, we put all of the cities on our stack at the same point in time, or at one point in time, which means that, and that happens if we had like sort of a linear graph. It goes one city to one city to one city to one city like that. That's one reason it's O of C. The second reason is because our visited set should contain all of the cities that are present in our graph by the time we're finished executing. So it uses O of C space. All right, that's all for this video, and I'll see you in the next one.